Welcome to the Problems channel, Season 2, Episode 15, the episode which I titled the Fourier series of the logarithm of the gamma function, because in this episode we will be solving the mathematical problem S2E15, in which we are challenged to decompose the logarithm of the gamma function into its Fourier series over the clopen subset of real numbers between 0 and 1. But before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to the channel. And second of all, it is a good idea for you to go to the home page of this channel and under the channel's trailer section, find the episode titled The Problems Channel How To, and watch that episode in its entirety and follow all the instructions given in that episode, because in that episode we explain and motivate everything that we do on this channel. As a fair warning, in this episode we will think like a mathematician a lot. I will write a lot, covering the board behind me right to left and top to bottom, but because unfortunately my board is not big enough, I will be erasing the material just covered quite often, which means that it is a good idea for you to grab a pen or two, grab a bunch of sheets of paper and tag along. But in order to improve the overall quality of the consumption of the material presented on this channel, do not worry about it. I will break this episode into a large number of small segments, each of which should be consumable in a straightforward manner, and that way you can pause this video and fast forward, or pause and rewind. And overall, if you were not able to solve this problem correctly on your own and completely, then do not worry about it too much. Do follow the instructions that we gave in Season 1, Episode 2. Go back and analyze the points where you failed and why you failed. But this problem in general is quite challenging, and at the same time, it is absolutely beautiful as well. We begin our beautiful journey with the traditional assumption that the single variable, real-to-real, 2-pi periodic function, designated as f of x over here, at the point x, can be decomposed into a corresponding infinite trigonometric series whose shape is shown over here, over the origin-centered interval of length 2 pi as depicted over here. We also assume that the corresponding infinite trigonometric series shown over here can be integrated term by term, and also we assume that if this relation shown over here is multiplied through by the corresponding cosine first and the corresponding sine next and separately, then the resultant trigonometric series can also be integrated term by term, and in that case the values or the overall shapes, the generally real numbers an and bn, can be recovered via the following integral formulas shown over here, where for the value of the coefficient an, the index n varies over all the non-negative whole numbers, and the index n for the coefficients bn varies over all positive whole numbers. In general, the numbers bn and an are taken to be real, but it is always possible to sprinkle the complex numbers in there later on if need be. But in general, if all these constraints are honored, then the numbers an and bn are called the Fourier coefficients, and the representation of the single variable real-to-real function f of x at the point x, shown over here, is called the Fourier series of that function over the origin-centered interval of length 2 pi. However, because we are looking to decompose our function logarithm of the gamma function over the clopen interval 0 to 1, the interesting question now is how can all this beautiful machinery can be morphed or transformed into the case where the function f of x is decomposed over the origin-centered interval of an arbitrary length 2L. And of course, we understand that this function will be 2L periodic. And we answered that question using one of the problem-solving approaches that we have covered already. And which problem-solving approach that is? Correct. That would be the mighty transform and conquer problem-solving approach, and it will dovetail into the process of answering that question as follows. Let's say we separate ourselves right now from this case, and the function f of x, a single variable real-to-real function f of x, which is generally different from this function over here, is such that it is defined on the interval that is origin-centered and of length 2L, where L is a strictly positive real number. And then how do we transform the machinery shown over here into this specific case? Well, it's not that difficult to see that we can, by hand, craft the following substitution or transformation. That is, if we say that, for example, x is equal to L over pi, and I will use the blue chalk over here for a new variable t here, x equals to L over pi t. L is a constant, strictly positive real number. Pi is a positive, strictly positive real number that is constant. So with this ratio, what do we have? If we put the right-hand side of this equality into our original two inequalities, then what shall we have? Well, then we will have negative L less than or equal to L over pi. Here we will have our new variable t, and this will be less than or equal to L. Then again, because L is a strictly positive constant real number, if we divide these two inequalities through by L, no change in signs will take place. So technically we cancel the L's over here, and because pi is a strictly positive real number, constant of course, if we multiply our two inequalities through by pi, the signs will not change, and we will have here what? Pi, t, and pi. In other words, let's write it down. We will have negative pi on one side, less than our new variable t, and less than pi. And in this case, by this quite straightforward transformation, we managed to morph our variable x, which right now sits between an origin-centered interval of an arbitrary length 2L, into the variable that sits in the origin-centered interval of the classical length 2 pi over here. And what does that mean? That means that our original single variable real-to-real function will now look as follows. F of L over pi, and then we'll write the new variable t over here like so, will be a new function, phi, let's say, phi of t, like so. And if you already see where this is going, then you can fast forward to the next segment. If you cannot work with these things on the fly, then let's spend a little bit more time together on this one. So now, because the variable t varies over the classical origin-centered interval of length 2 pi, and we call that function phi of t, for example, then we know already, under all the appropriate assumptions, what will its Fourier series look like if we write it down. Then what will we have for the function phi of t? For the function phi of t, we will have phi of t. Let me write it down with the blue chalk. I'm sorry, here, t, like so. What will we have? We will have the same initial coefficient a, which is traditionally divided by 2 for the reasons of symmetry. and then we will have plus the infinite sum that runs between 1 and positive infinity. We'll have our coefficients an times what? Cosine of n. But now, which variable do we use over here? Not x, but our new variable t that is not misbehaving, and plus the coefficient b sub n times sine of n times what? Again, our coefficient, our new variable t, shown like here, like this, and consequently, we pretty much rewrote what we had over here, but in terms of our new function, single variable, real to real, phi of t, and pretty much verbatim, we can write down the coefficients for this. Let me write it down over here. For the coefficients a sub n and b sub n, I'll use one expression, 1 over pi will be integral from negative pi to positive pi of the function phi of what? It will be phi of t times, for the an on the top, we will have the cosine of n t dt. Again, I'll just highlight it here so it's easier to see. And for the coefficient bn, we'll have sine of n t dt. And that notation should be straightforward. For the second floor, we take the expressions for the coefficient an. For the bottom floor, we take the expressions for the coefficient bn. Obviously, for coefficient n, we have what variance? Here, n will vary from 0, 1, 2, 3, and so on. And for the coefficient bn, n will vary as 1, 2, 3, and so on. So here we did not do actually anything new or earth-shattering. We simply rewrote what we had already in the classical case of the origin-centered interval of the length 2 pi for our function called phi of t. Now, as the transform and conquer problem-solving approach prescribes, what do we do next? Exactly, we do reverse transformation. In this case, in other words, if we go back through our original transformation and write down that t is equal to what? T is equal to pi over L x, then what will happen then? Well, for our decomposition of the function f of x over its Fourier series, we'll have still the same coefficient a0 over 2, plus we will have our infinite sum that runs from 1 to positive infinity. Again, nothing new here, an cosine of what? Now we have to be careful. Here we have n times t, but now t is taken from the reverse transformation. So here we write n pi over L x plus bn times sine of what? N pi x over L. So that much should be understood. That transformation should be, that step from here to here should be straightforward. We simply used the reverse transformation as the transform and conquer problem solving approach prescribes. And we are almost home free. So the only thing we have to do now is what? We just have to write down the portraits, so to speak, the integral portraits of our coefficients an and bn, and that is straightforward to do. Let us do that over here at the bottom. Let's write it down for the coefficient a sub n. What will we have? Let's think about it together in an expedient manner. The differential dt, and that is why I highlighted with a different color, the differential dt in this case becomes what? Pi is a constant real number. L is a constant real number. Their ratio is a constant real number. It can be carried from under the differential. That's one. Number two, because it is a constant, it can also be carried from under the integral sign. But here we will have what? Pi over L. Pi in the numerator, pi in the denominator. Pi and pi cancel out. What will we have? Exactly, we will have 1 over L. This is our requirement over here. L is strictly positive real number. Here we will write the integral that runs from where to where. Technically, if, for example, t on that side over here becomes negative pi, pi and pi cancel out, x becomes negative L, but using the property of definite Riemann integrals, we will write down, for example, this integral like so: from real number rho to rho plus 2L. I will explain what these real numbers are. Rho is a real number, so on the bottom, the lower boundary of integration, we have an arbitrary real number rho. The top boundary is rho plus 2L. And what do we have over here in the expression for the integrand? Well, f phi of t becomes this expression, but with the substitution for t, it becomes f of x. So we write down our expression f of x times cosine of, now we have to be careful, n t, and t is pi over L times x. So what do we have over here? We have n pi x over L dx, and the corresponding expression for the coefficients, for coefficient bn will be the same thing, 1 over L integral for any real number rho to rho plus 2L. Then again, we will have our function f of x times sine of what? N pi x over L dx. Technically, this will hold for any real number, rho. And that may sound a little bit mysterious to some of our viewers, but there is really nothing mysterious over here. Traditionally, in many textbooks, for example, you will see from the boundaries of integration for the coefficient an and the coefficient bn will vary from negative L to positive L, but because our function is 2L periodic, in other words, in our case, let's say we separate this here, we'll say f of x plus 2L equals f of x everywhere, of course, where the function f of x is defined. And then using the standard property of Riemann, definite Riemann integrals, where should I write it? Well, maybe let me squeeze it over here so you guys understand what's going on. In this case, we have the following result. The integral from rho to rho plus 2L f of x dx equals to integral from 0 to 2L f of x dx. This right here, this is one of the early theorems that is proven in the, for example, real analysis course. It's not too difficult to generate a proof of this theorem. We simply break this interval into 3, make the corresponding substitution, and voila, we have it here. But fundamentally, this is the shape of the Fourier coefficients an and bn for a single variable real-to-real function f of x that is defined on the origin-centered interval of an arbitrary length 2L, where L is a strictly positive real number. And precisely because of this property of periodic functions right here, This property tells us what? This property tells us that the value of the integral of such a function does not really depend on the specific boundaries that delineate an interval of the length 2L. And all these integrals have one and the same name captured over here, an integral from 0 to 2L of f of x dx, and this is precisely what we have here on the bottom. Consequently, we will just remind ourselves that over here, the index n varies starting from 0, and then it runs 1, 2, 3, and so on. And the four coefficients bn, the index varies over here starting from 1, 2, 3, and so on. Again, this transition should not cause any problems for those who studied the transform and conquer problem solving approach. For us, this is the classical encore appearance of this problem solving approach in grown up academic material. In briefly, that means what? Problem, transform, solve, and reverse transform. This is precisely what we have over here. And once we understand where all these expressions came from, we can now take on precisely the Fourier series of the logarithm of the gamma function, which we will do next. Now that we understand where and why did the formulas shown at the bottom of the board come from, how they were obtained, we go back to our function, the logarithm of the gamma function, and we craft the battle plan for that function. And what does that mean? Well, because we're seeking the Fourier series decomposition of the logarithm of the gamma function over the clopen subset of real numbers between 0 and 1, where the 0 is excluded and 1 is included. That means what? That means that if that interval is of length 2L, that means that the value of L is what? 1/2. And if we put 1/2 over here for the coefficients an and bn, what will we have? We will have 2 as shown over here, and over here we'll have 2 in front of both integrals. And for the value of the argument of the trigonometric functions of cosine and sine, what will we have? Well, if we have L in the denominator, flip 2 into the numerator, 2n pi x, 2n pi x, 2n pi x, 2n pi x. The shape of the function f of x is the logarithm of the gamma function. It's all very straightforward, no mystery here. And consequently, the representation of the logarithm of the gamma function over the said interval as the Fourier series is shown over here. Again, we have one and the same initial coefficient a0 divided by 2, and the rest of the series shown over here. The values or the portraits of the real numbers, in this case an and bn, is what we will fight with next. But the cosine and the sine, the trigonometric functions cosine and sine over here, have the well understood and predictable arguments, 2n pi x in the first case and 2n pi x in the second case. And before we move on, I would like to say just one more thing, that everything shown on the board over here may look very strange, perhaps even scary, and may come across as a perfect symbolic storm, but this is precisely the thing about mathematics. This is not mathematics mostly. What mathematics was is the play of thought, because mathematics, among other things, is a play of thought. And what was our play of thought? Our play of thought was to generate this happy idea to invoke, so to speak, the transform and conquer problem solving approach. Once we realize that that is the proper direction to go in, the rest of the stuff comes out and happens in some sense naturally. And we need neither be afraid of it, nor we need to memorize it. There is no need to memorize all of this. This is the basic idea, if anything else, that we may need to memorize, and everything else, and that is mathematics. And whatever happens after that idea is, in some sense, is not mathematics, but what happens after mathematics happens and takes place, the play of thought. And come to think of it, for example, I have studied all this material more than 30 years ago, and if I recall correctly, back for the Fourier Analysis course back in the time, I had the perfect A, not because I'm so clever, but because precisely I realized back then that all I have to do is understand the essence and small number of essential technical ideas, and the rest of this symbolic storm comes about and happens almost naturally and almost by itself. But in the next segment, now that we know the portraits, now that the shapes of the coefficients, the Fourier coefficients an and bn for the logarithm of the gamma function on the clopen subset of real numbers has been revealed, and we understand the trace, we understand the genesis, how did this come about, we now step into the ring, throw our head in, cross the blades with the pirate, so to speak, and now we will one by one deal with the coefficient a sub n. First we will take this guy on, and then we will fight the fight with the coefficient bn next. In this episode we will recover the shape of the Fourier coefficients a, n, and if you are witnessing this for the first time in your life, then what is about to happen, as a spoiler alert, should be both breathtaking and quite amazing on the one hand. On the other hand, this is what mathematics is about, and these things happen in mathematics quite often. That is, in order to recover the shape of the Fourier coefficient a sub n, we will avoid a direct or head-on fight with the integral that I wrote down in the previous segment, and we will think like a mathematician and we will do something else. And as a side remark, do not worry about the actual shape of the integral that is associated with the Fourier coefficient an, because on the one hand you should be able to recreate it and write it down just by looking at what's shown over here on the board. On the other hand, I will write down these expressions again when it's needed at the crucial moment. That is, here we will avoid a direct head-on collision with the integral. That is the name of the Fourier coefficient an, and instead what will we do? Think about it on your own. You may put this video on pause, come back, and the idea, a happy thought that you should be able to generate is the following. We will hijack precisely the decomposition of the logarithm of the gamma function shown over here. And what other important ingredient we will need for that? Exactly, in some sense, this will be again the transform and conquer problem solving approach that will take the shape this time in the form of what? The so-called reflection formula for the gamma function. Recall that this is in general holds for the corresponding complex numbers, but for now we'll keep things simple. For all real numbers x, it is the case that gamma of x times gamma of 1 minus x equals to what? Pi over sine, the trigonometric function of sine pi times x, and that formula holds for all x or complex numbers, this time real numbers that are not whole numbers. Now, what next transformation should we apply to this reflection formula? If we think about it, then multiplying the numerator by 2 and multiplying the denominator by 2 will do what we need to be done. And why is that? Well, what is the next step after this happy thought visited us? Again, notice that mathematics is a play of thought. That was a play of thought. Avoid the head-on collision with the integral. Try to craft or try to blaze an alternate path for the recovery of the name and the shape of the Fourier coefficient an, and do what over here? Exactly, we logarithmicize this expression over here, and we use the famous property of real numbers, for example, I'll write it down so we don't take too much space. For all real numbers appropriately defined, x times y equals log of x times plus log of y. I will not write down the specifics for the values. We'll understand what these numbers are. They're supposed to be strictly positive real numbers, and in some sense you may know about this expression from middle school, depending on the mathematical curriculum that you took, or maybe from high school. And in the grown-up fashion, what sits over here is an isomorphism between certain groups. Now, if we take this tactical expression and apply it to this one, what will we have? We will have the logarithm of the gamma function of x plus the logarithm of the gamma function of reflected argument equals logarithm of 2 pi minus, so far so good, because we can represent this as 2 pi times 1 over, so minus logarithm of 2 sine of pi x. So far so good. So we simply took the reflection formula that holds for all real numbers such that we logarithmicized it. We use the fundamental property of the logarithmic function, obtained this expression, and now what do we see? What is the next tactical maneuver? Well, here is the next idea, also in some sense the one that hails from the transform and conquer problem solving approach. And what that is, well, this is exactly how we hijack this guy right here. The Fourier series of the logarithm of the gamma function evaluated at the argument 1 minus x can be obtained from the corresponding Fourier series of the logarithm of the gamma function evaluated at the point x if we do what? If we do the following transformation. X in this case and in this case becomes what? 1 minus x. You see, this is another beautiful and straightforward transformation. And in that case, what will we have for the, if we apply this transformation uniformly to the expression shown over here, then what shall we have? Let me write down some helper material over here. Let's think about this together. If in the case of the cosine, of 2n pi 1 minus x, what shall we have? We will have cosine of 2n pi minus, we will have the cosine of 2n pi minus 2n pi x. And what does this expression tell us? Well, precisely because the trigonometric function of cosine is even, this guy, the integral multiple of 2 pi, because the trigonometric function of cosine is 2 pi periodic, can be dropped with no ill effect. And because the trigonometric function of cosine is even, that means what? Cosine of negative 2n pi x becomes what? It becomes, let's write it down here, it becomes cosine of 2n pi x. And once we have this on the books, we already see what will happen if we apply this transformation to the trigonometric function of sine. If you can handle it, then good for you. You can fast forward to the next step, but here we will write it down just to be pedantic. Sine of 2n pi with the transformation 1 minus x applied to this summand right here, we will have what? We will, let me just delineate this. We'll step down over here. We will have negative sine of 2n pi x. So far, so good. This is nothing more than the proverbial upper middle school or high school manipulation. Nothing is going on over here mysterious. We're simply using the fact that both the trigonometric function of cosine and the trigonometric function of sine are 2 pi periodic, but the function of cosine is even and the function of sine is odd. That is why the negative sign jumps over here from negative to n pi x over here. So far, so good. Now, under this beautiful and straightforward transformation, let us write down the expression for the expected Fourier series of our function logarithm of gamma evaluated at 1 minus x. What will we have? The initial coefficients will be the same, a over 2. Then we will have our sum that runs from 1 to positive infinity. And then we will have a sub n times cosine of 2n pi x. This is due to this step right here, straightforward step. But for the coefficients bn, we'll have negative minus bn sine of 2n pi x. So far, so good. So this transformation obtained from this expression via this transformation. And now what do? Since here we have a sum, we sum this expression in this expression. And what do we have? Well, let's write it down. The logarithm of gamma function at x plus the logarithm of the gamma function evaluated at 1 minus x equals a0 over 2 plus a0 over 2 will be what? Very good. It will be a0 plus the summands with cosines will double up. This summand with this summand will become what? It will become the sum and runs from 1 to positive infinity. And here we will have 2 times a n times cosine 2n pi x minus or plus what will happen over here, positive bn sine 2n pi x minus bn, exactly the same term. So here we will have a big fat 0, and let me grab a new piece of chalk. And what we have over here is a sum that on the one hand we obtained by applying this transformation to this function over here. On the other hand, we know that this expression right here and the expression we obtained over here by logarithmicizing the reflection formula. See, this is the beautiful play of thought. This is where mathematics happens in some sense. The play of thought. Logarithmicize the reflection formula. Bam, obtain 2 summands. Transform the logarithm of the gamma function like so. Expand it into its expected Fourier series. Sum these 2 bad puppies. Obtain the same expression. But this sum and this sum are what? One and the same sum. That means that if the left-hand sides of these 2 equalities are the same, it means that the right-hand sides of these equalities are the same. So now we juxtapose the right-hand side over here against the right-hand side, over here. And what do we see? Exactly. We see that this number over here is a constant, and this number over here is a constant. And what is this infinite, technically trigonometric series? But in most general case, that is what? That is a functional series, because here we have a function, a trigonometric function of cosine. So this guy must be equal to this, because this is another function of x. So now just by juxtaposing these 2 right-hand sides of these 2 equalities, what kind of conclusion can we make right away? Well, this bad puppy over here must be none other than this. So let's write it down over here. Don't worry, I'll write it down again. Let's say I'll write it over here. A sub 0 must be what? Must be the logarithm of 2 pi. So far, so good. By juxtaposing this against this, we see the only constants over here are these. So this must be it. And if we divide this guy by 2, as will be needed over here, what will happen? If we divide this guy by 2, what will happen? Very good. We will just slug in the square root over here. Bam. Done. The first summoned in the expected Fourier series decomposition of the logarithm of the gamma function over the clopen subset of real numbers was revealed almost instantly, and it happens to be the logarithm over base e, right, e the Euler's number, of square root of 2 pi. Isn't that wonderful? Now comes the next question. What is this series right here? This guy. What is the name? If we compare it to this guy. So by the looks of it, what shall we say? We have that this sum must be equal to, let me write it down over here, minus logarithm of what? Of 2 sine of pi x. These are our only choices over here. So far, so good. And that is why at the end of the previous episode, I gave you guys these two hints. One, I asked you to prove this formula over here, the reflection one. So we use it here in the first step. And I also ask you to find a way to recover shapes of certain infinite trigonometric series. And this is where the helpful step comes in. For example, this little, again, it can be treated as a heuristic template because it's not really an algorithm, but the Swiss mathematician Leonard Euler and the French mathematician Lagrange, if I'm not mistaken, they use this method / approach to sum this series. And we will do that in the future at some point, but it can be shown using this method that minus logarithm of 2 of sine x over 2 is none other than the sum of cosine of n pi over n, where n varies from 1 to positive infinity. This, for example, series, this expression can be read right to left, meaning this is unknown, this is known, and there is a miniature industrial strength method that allows us to recover the shape of this function that Euler and Lagrange used it many years ago. And this expansion holds for what? For all real numbers such that strictly x is greater than 0 and less than 2 pi. So now we'll look at what we have. We'll look at what we have, this series against this one, and what we know, for example, can happen. So how can we transform this result into what we have over here? Well, that is another transformation, and that transformation is quite simple. I will do that in the next segment because I will just erase some of the material that I already covered, so this result looks more tolerable and more digestible. Very well, the kindergarten variety material that you guys saw on the right hand side of your screen on the board over here, I erased, and here I simply wrote down so that it's easier to consume and easier to comprehend. Basically, this idea I lifted up over here. Again, yet another instance of the wonderful transform and conquer problem solving approach. We know that due to the miniature industrial strength method used by, for example, Leonard Euler to sum the infinite trigonometric series with diminishing coefficients over here, we know that for all positive real numbers x that sit strictly between 0 and 2 pi, meaning that neither 0 nor 2 pi is included, the following expansion holds. And I showed that deduction actually some number of years ago on Quora. So once we have this, we compare or juxtapose what we have against what we need, and what do we see? How can we manufacture pi times x in this expansion over here from what we have over here? Well, the straightforward transformation, I showed it for your convenience in blue over here. In other words, we come to a previously obtained result, transform it result based on this thing over here, 2 pi x, replace x with 2 pi x uniformly everywhere in this result, and what do I obtain? Well, if x becomes 2 pi x, 2 and 2 cancel each other, we get pi x. So on the left hand side we have negative log of 2 times sine of pi x, and this is precisely what we have over here, this term right here, this summand right here. And what do we have on the right hand side of the prepackaged result? I apologize, I made a typo over here. Pi n pi, it's not n pi, it's nx, of course. So the argument of the trigonometric function of cosine in this expansion is x and x. So here x becomes 2 pi x. So that means that the argument of the trigonometric function of cosine becomes 2n pi x. Wonderful. And in the denominator, we still have our n. The sum rolls from 1 to positive infinity. And again, if we juxtapose what we have in the prepackaged result, slightly transformed, with what we need over here, what can we write? Well, the shape of the trigonometric function of cosine is exactly the same, 2n pi x in what we have, and 2n pi x in what we have in the prepackaged result. Isn't that wonderful? Absolutely wonderful. Consequently, the multiplicative factor over here, this guy, 2n, must be what? It must be 1 over n. In other words, we'll get a little fancy, so we'll say for all n greater than 0, what do we have? We have 2 times an. We have 2 times an equals 1 over n. Isn't that wonderful? That means that we simply, again, divide both sides of this equality by 2. And what do we have? For all n greater than 0, an is 1 over 2n. This is another result. And the value of the initial Fourier coefficient a0 we recovered over here in this section right here. Don't worry about it. I'll make it neat and nice in the next segment in a few seconds. But overall, we now step back and digest what just transpired. We took the original expression for the expected shape of the Fourier series of the logarithm of the gamma function on the clopen subset of real numbers. From our web of mathematical knowledge, we yanked a wonderful reflection formula. We logarithmicized it. We transformed the Fourier series of the logarithm of the gamma function into the second term over here. We added the new expansion to the existing one. We witnessed how the trigonometric function of sine bound terms canceled each other. We've got 2 copies of the same coefficient a sub n. Then we equated the 2 sides. We recovered the value of the constant coefficient a sub 0, and then by knowing about the prepackaged result, we made another straightforward transformation, obtained the expression for the trigonometric function of cosine. It happened to be the same as what we have over here, and we deduced the value of the Fourier coefficient an for all n that are greater than 0. So obviously we're dividing by n, but we cannot divide by 0. So for all n greater than 0, meaning 1, 2, 3, 4, 5, and so on, this is the expression. This is the initial value. Problem solved without without fighting the fight with the integral that we are about to discuss in the next segment. This segment is optional, it's for curious travelers only, as an extra for experts. If you're not interested, feel free to fast forward to the next segment of this episode. But here, as a reminder, the actual integral shape of the Fourier coefficient an was this one that is shown over here. And when, for example, we substitute the value of n equal to 0 into it, we see that the cosine of 0 will be 1. This whole messy argument here will collapse into positive unity. And what we will have, as I depicted over here, the value of the coefficient a0 as twice this integral. And this integral over here actually is known as Raabe or Raabe Integral, named after the Swiss-born, if I'm not mistaken, mathematician named Joseph Ludwig Raabe. This is how his name is spelled again, if I'm not mistaken. And the thing is that in the case when the value of the index n for the Fourier coefficient an is 0, this integral can actually be computed in a elementary fashion. Again, some years ago, I wrote up the deduction for this, for the evaluation of this integral. It's not that complicated. And again, as you can see, what we will do over here, we will do precisely the substitution over here of what kind. We will say we'll take x into 1 minus x. And once we bake the gamma function of 1 minus x, what we will do? Precisely, we will add the two integrals. We will get the product of gamma of 1 minus x times gamma of x. This is our favorite reflection formula, pi over sine of pi. The logarithm of the trigonometric function of sine, the integral in the appropriate boundaries is very well known. Again, its evaluation is courtesy of the Swiss mathematician Leonhard Euler. This is a notorious, fairly well-known integral, but that's basically the evaluation path is quite transparent. Again, substitution, reflection, and then the log sin integral. So this can be evaluated in a straightforward manner. Again, its value is the logarithm in base e of square root of 2 pi. Obviously, here we have the coefficient 2 for this guy. And in general, again, as a historical background of not maybe much significant to us, but for general education, the Joseph Ludwig Raabe also considered this integral, where the boundaries of integration are basically for any positive, strictly positive real number, go from here to here, basically unit length intervals for this integrand, the logarithm of the gamma function. This is the result. Again, it's not too difficult to obtain. It can be done. If you guys show any interest, maybe I'll put an episode together for the deduction of this result and this result. But generally, this is what we have when we parameterize, so to speak, where this one, the unit length interval slides over the real axis. And obviously, when, for example, if we want to put the value of a equal to 0, then we'll have to take the limit. And from your real analysis course, you probably remember very well, x times log x, the limit of when x tends to 0 is 0. So all these things evaporate, and we have this case over here. All these things converge nicely. But again, as a overall technical adventure, do notice that we avoided the fight with we avoided an explicit fight with the integral. And amazingly enough, in some sense, we obtain the value of this integral without doing the proper integration through the mechanics that we showed in the last segment. We deduced that a0 over 2 is precisely the logarithm in base e of square root of 2 times pi, and for all n greater than 0, 1, 2, and 3, so on, this is the value of the Fourier coefficient of our function. So in some sense, we already know this term, and we already know this term. So now we have to fight the last fight. And in this case, this time, this will take us a little bit of time again. We'll lay down some chalk dust. But this time, with the Fourier coefficient Bn, we will take on the corresponding integral, and that is what we will do next. In the previous segments, using a fairly small number of fairly clever transformations, we avoided a direct fight with the integral shown over here, but nonetheless, and this is one of the amazing things in mathematics, we still managed to recover the names of the real numbers that hide behind this integral. In the first case, for the initial value of the Fourier coefficient a0 over 2, we learned that when n is equals to 0, then we obtain the so-called classical Raabe integral of the logarithm of the gamma function, and the value of that integral is equal to logarithm of the square root of 2 pi. And for all positive whole numbers, the value of this integral came out to be, amazingly enough, as a rational function in n, 1 over 4n. And in order to give you some visuals of the integrand, not the integral as the whole thing, but just the integrand, then here is a plot of the first initial small number of integrands over here that I did with the free software called GeoGebra. In contrast, in order to reveal the portrait of the Fourier coefficients Bn, we will pick a direct fight with the integral shown over here. We will cross the blades with the pirate, so to speak. But before we do that, using the free software called GeoGebra, here are the plots of the relevant integrands for the initial small number of values of n. The overall battle plan over here is to recall the following integral representation of the logarithm of the gamma function, and then substitute that integral representation into the formula for the Fourier coefficients Bn, and switch the order of integration in the resulted iterated integral. Before we do that, however, we will work with the integral representation of the logarithm of the gamma function shown over here. The formula shown over here for the integral representation of the logarithm of the gamma function may look a little intimidating and a little scary, but there is no need to be afraid of that formula, because in general it can be deduced in a fairly straightforward and basically or essentially elementary manner by constructing the difference between the gamma function and the beta function, like so, and then morphing this difference using the corresponding formula that connects the beta function with the ratio of the product and the sum of the gamma function, tending the value of the parameter b to 0 and so on. And if there is enough interest in our community, I may put together an episode that shows the relevant deduction, but this is not something to be afraid of. This can be done again, but for now, the interest for us, before we substitute this integral into the formula for the Fourier coefficients Bn, we need to massage this object a little bit to make it more digestible. In other words, what do you think the next step in our manipulations should be, and what kind of substitution would you make in this case? You can put this video on pause, think about it. When you come back, it should be evident that the exponential substitution is practically begging to be made. In other words, in this case, we put the e to the negative power of z. We set it as t. This will be our new dummy integration variable. And then from here, it follows what? Z. From here, we have that z, for example, equals to negative logarithm of t. And then if we differentiate, we take the first differential of this expression, what do we get? We get dz equals to -1 over t, and then dt. That maneuver is also straightforward from here to here. We apply the first differential to the left-hand side of this equality, to the right-hand side of this equality, and obtain this result. And under that substitution over here, what do we have? If we use this substitution, what shall we have? Let's work with this together. When at the lower boundary of integration z is equal to 0, then t is equal to 1. So we obtain the integral from 1. When the variable z grows without bound and tends to positive infinity, then this exponent diminishes, and in the limit it vanishes. So we have 0 for the upper boundary of integration. And then let us work with the integrand over here. What shall we have here? Well, x minus 1 stays x minus 1. E to the power negative z becomes t. Minus, we have the ratio of what? E to the power minus z is t. E to the power minus x times z is what? Minus t to the power of x. Evidently, 1 minus e to the power negative z becomes 1 minus t, like so. Then we close the parentheses. Then we carefully write down 1 over z becomes negative logarithm of t, and dz becomes negative 1 over t dt. Negative times negative becomes positive. These two zeros annihilate each other. And what do we have? We have in the positive dt in the numerator, and in the denominator, what do we have? We have t times logarithm of t. Now let us carefully massage this result further a little bit. It's not that complicated. See this t over here in the denominator? So this t in the denominator will cancel with what? In this parenthesis, it will cancel with this copy of t, with this copy of t. So here we will have 1, and 1 copy of t over here. So this will become -1. Also, let us switch the order of the boundaries or the direction of integration. Instead of moving from 0 to 1, we will move, instead of moving from 1 to 0, we will move from 0 to 1, and we'll flip the sign over here. And what shall we have then in this case? Finally, what is the shape of the integral that we will have? It will be integral from 0 to 1. We'll have 1 minus t to the power x minus 1 over 1 minus t minus, so this minus became plus, and we have a minus in front over here, minus x plus 1. And what do we have still here? We have dt over log of t. This is our final shape for the, again, a different integral representation of the logarithm of the gamma function. And now we take this representation shown over here, and what do we do with it? We inject it all the way over here, and then we morph the resultant object into the iterated integral by switching the order of integration. Evidently, we will keep dt over logarithm of t as on one side, and this parenthesis we will glue to the sign of the 2n pi x, and I will do that in the next segment. In the previous segment, we massaged a certain integral representation of the logarithm of the gamma function, and we switched the order of integration in the formula for the Fourier coefficients bn by moving this parenthesis from the first integral from the outer integral into the inner integral, and that switch of order of integration can be done and is legal in this case for the following reasons. The expression shown over here as a function of two variables, x and t, on the interval 0 to 1 is continuous everywhere except at the point t equals 0. At the point t equals 0, that function is function of two variables loses its continuity. However, the integral of this expression with respect to the variable t converges uniformly with respect to the variable x for all x inside the interval 0 to 1, and that can be shown with the following estimate for the absolute value of this integral. If we take any real number tau such that it sits strictly between 0 and 1, then for the absolute value of the respective integral, we can write down the following estimate. The integral from 0 to tau of, what do we have, 1 minus t to the power x minus 1 over 1 minus t minus, we will write it like so, 1 minus x. Here we'll take the absolute value of the sine 2n pi x over absolute value of the logarithm of t, and here we will integrate dt. We pay attention here, it's not dx, it's dt. And we want to make sure that we want to show that this integral, the absolute value of this integral, can be bound from above as follows. 1 over 1 minus tau over 1 over absolute value of the logarithm of tau times absolute value of sine of 2n pi x, absolute value over x times tau x. And all this beautiful mass over here, for example, we can recognize the following limit over here. Divide this thing over here by 2n pi, multiply by 2n pi. When x gets fairly small, we recognize our favorite limit. So from above, this expression will be estimated as follows. 1 minus tau times 1 over absolute value of logarithm of tau times 2 n pi. And by the corresponding real analysis theorem, that means that the switch in the order of integration shown over here is legal. And next we will start working with the innermost integral shown over here. What we have done in the previous segment is a necessary evil, so to speak. There are cases when switching the order of integration is not allowed and it can lead into all sorts of trouble, and unfortunately many times the youngest students of mathematics especially neglect to do that. But if you want to run with the grown-ups, so to speak, you have to do it every time, even in the cases where you think it's obvious, because obvious is the most dangerous word in all of mathematics. Now that we justified the right to switch the order of integration in our case, we work with the innermost integral and we pick the easiest phase first. Here we will evaluate the integral that deals with just the trigonometric function of sine, and how many times we will meet this integral. Well, we will meet it twice. One when we multiply it by 1 over here, and once when we multiply it by 1 over here. The reciprocal of 1 minus t combined with this integral doesn't matter, so we will see this integral twice. This integral is a typical proverbial upper middle school variety. It's not complicated. If you see what's going on, fast forward to the next segment, but for the benefit of the majority of the audience, we will take it on explicitly. So here, once we multiply the trigonometric function of sine by 1 over here and by 1 over here, what shall we have? We will have the integral from 0 to 1 of the trigonometric function of sine 2n pi x dx. We can write down the result right away. It will be negative 1 over 2n pi, then it will be cosine of 2n pi x evaluated between 1 and 0. And luckily, the integral, any integral multiple of 2 pi will produce 1, the positive unity. So in both cases, we will have, barring the multiplicative constant over here, we'll have 1 minus 1. That will be 0. That is good news. This integral vanishes essentially, and because these things tend to get pretty hairy pretty fast, we will maintain the shape of the Fourier coefficient Bn as we go along. So now that we proved that this integral shown over here vanishes in both cases, what will we have for the shape of the inner integral? We will have just the negative x and just the negative. Let me just be more polite and just say that it will be negative. It will be minus sign over here, minus this thing, and then minus x as this. And then obviously, as the next candidate, we'll take on the integral, which is essentially a product of the trigonometric function of sine and a polynomial in x. In the next step, we compute the integral from 0 to 1 of the trigonometric function of sine times, in general, a polynomial in x. And these types of integrals are always computable in closed form or as finite combinations of elementary functions using the technique known as integration by parts. And it is quite evident what should we do over here. Those of our viewers who see what is going on can skip forward, but for the benefit of the majority, again, we show the relevant computation in its complete form, 2n pi x dx. Here it is evident that we choose this part to be the proverbial dv. This part x becomes u. In the next stage, du becomes dx and evaporates. That's how we gain our tactical win. But in general, what we will have over here, first we will have negative x over 2n pi times cosine of 2n pi x evaluated between 0 and 1 minus times negative 1 over 2n pi becomes a plus. So here we'll have plus 1 over 2n pi, and the integral runs from 0 to 1 of cosine of 2n pi x dx. Here, when the trigonometric function of cosine is evaluated, any integral multiple of 2 pi, which is what we have here in both cases, we obtain 1. And at the upper boundary, the value of x is 1. At the lower boundary, that summand evaporates. So here we have negative 1 over 2n pi plus 1 over 4n square pi square times the value of the trigonometric function of sine evaluated at 2n pi x between 0 and 1. Here we get lucky again because the value of the trigonometric function of sine evaluated at any integral multiple of 2 pi is 0. So on both ends, this summand disappears. It vanishes, and the only summand that does survive is minus 1 over 2n pi. And we remember that here that polynomial times the trigonometric function of sine is taken with the negative sign. So negative sign times the negative sign. It percolates into the integral shown over here with a positive sign as 1 over 2n pi. because we maintain the shape of the Fourier coefficients Bn at every step that we make, so it's easier to keep track of these things. Here, as we have shown in the previous segment, the polynomial times the trigonometric function of sine became 1 over 2n pi, and here I maintain the result. I use the square brackets with no special meaning, just as a visual candy or as an eye candy to separate the results, but now this summand over here relates to this integral, and now we only need to attack this guy right here. This is the integral that runs from 0 to 1, t to the power x minus 1 times the trigonometric function of sine of the argument 2n pi x. And remember that a reciprocal of 1 minus t was there in that fraction, but because nothing over here depends on x, we carried it out from under the integral sign. And here, in order to save us some time, I already wrote down some prepackaged result that we will need. So here, with this integral, it is evident that what next step should we make? Correct. Here, with this integral, we should convert the expression t to the power of x minus 1 to its exponential representation. One copy of t, the negative 1 over here, can be carried out from under the integral sign. And then we will have the integral from 0 to 1 e to the power of x logarithm of t. That transition should be evident. From t to the power of x, we came to its exponential equivalent. And then we have our favorite function, sine of 2n pi x dx over here. And at this point, we will be using a quite popular integral that we will actually pay special attention to this guy shown right here. It's, for now, we will treat it as a previously solved problem, but in the near future, we will come back to this integral when we will study the idea of one fixed problem, in some sense, many different solutions, and we will evaluate this integral and its close cousin, for example, using the ordinary differential equation of order 3. But for now, do not worry about it. We'll take this as a known prepackaged result. And in this case, what do we have? In this case, this we have bx, so this factor becomes a constant b, 2n pi becomes b in this integral, and the parameter a in this integral becomes what? It becomes this guy, the logarithm of t. I'll circle it, becomes a. That much should be evident and transparent. A is the logarithm of t. B is the expression 2 times n times pi. And now we simply use the prepackaged result and write down what will happen once the boundaries of integration are taken into account. E to the power of ax becomes, again, e to the power of x times log of t. So we come back to the expression in its form to make it easier to compute, tx times. Here we will have a times the value of the trigonometric function of sine of bx. So here we will have a in the numerator, logarithm of t times sine of 2n pi x minus the value of b, which is 2n pi times cosine of 2n pi x over all this long expression over here is divided by the sum of squares, which is logarithm square of t plus 4n square pi square, and all this stuff is evaluated from 0 to 1. And what will we have in this case? Let us compute carefully. 1 over t will remain always. 1 over t remains. And we will also have the denominator here in all cases. It doesn't matter, so we can write this guy down right away. It will always be here. Logarithm squared of t plus 4n squared pi squared will remain over here. Now let's carefully evaluate the numerator over here at the boundary of 1. Here, in either case, we again get lucky. The value of the trigonometric function of sine at both boundaries, upper and lower, evaporates. We're not going to have this summon to worry about. At the upper boundary of 1, we will have the value of t. We will have the value of t for one case. And in this case, we will have 2 and cosine at 2n pi will be 0. So this will collapse into t times negative 2n pi for the upper boundary of 1. T to the power of 1t, 0, negative and pi. Subtracting from this whole thing, again, the values of the numerator at 0, sine evaporates. This, again, becomes unity, positive unity. The 2n pi is taken with the negative sign, but because we are subtracting at the lower boundary, this becomes with the positive power 2n pi, and the value of t raised to the power of 0 becomes 1. In other words, here we write what? We write plus 2n pi is what survives from this integral over here. And in the next segment, we will arrange this result more neatly. Here I moved the result that we obtained in the previous segment into the overall expression for the Fourier series of the Fourier coefficients Bn. We had 1 minus t in the numerator, and I just kept it so we can see what is going on here. Minus 1 minus t and 1 minus t cancel out, so we can carefully erase this factor over here altogether and this factor here, and what we have in the result is this final expression for the Fourier coefficients Bn. And in this case, when you look at this integral right now, this is pretty much the way the iterated integrals work. The variable x now is gone, and what we have left is the expression that contains only the dumb integration variable t, dt integral from 0 to 1, two of them, over the variable t of the reciprocal of the logarithm of t, plus this expression shown over here in square brackets. Again, there is only t and t over here. And the next question for you guys is the following. If you were doing this, what kind of substitution, what kind of next step will you take over here? Well, there are possibly different ways to proceed over here. Here is one way. We introduce the substitution that goes the other way. T equals e to the power minus 2n pi u, where u is our new integration variable. Then from here we trivially, what do we have? The logarithm of t becomes what? Negative 2n pi u. And what is dt? dt becomes negative 2n pi e to the power negative 2n pi u du. This is our substitution. And now once we apply this substitution to this integral over here, we will put the equal sign over here, and don't worry about it. Again, I will move things around so you will have time to maintain. your records, but for now we will step over here. So what do we have in this case? Well, first of all, at the lower boundary of integration of 0, when t is 0, then our new variable must be infinitely large, so it will tend to positive infinity. And when t is 1, this clearly will be 0. So that is what we have. So far we have, let's write it over here, 2 copies of the integral that runs from, again, if this is 0, then this is positive infinity, from positive infinity to 0. And then what do we have? The first summand over here will remain the same. So we will write it down as follows: 1 over 2n pi minus, in the numerator we still have our 2n pi in the numerator as it was. Reciprocal of t becomes e to the positive power 2n pi, so we can write it over here, e to the power 2n pi u. Again, this contribution is given by reciprocal of t over here. And here I forgot the parenthesis over here to be neat over here. So then for the square of the natural logarithm of t, what do we have? 4n square pi square u square. That is straightforward enough. So we have 4n square pi square u square plus, over there we have a constant, 4n square pi square, and this is it for our square bracket. We'll delineate it like this. And what do we have over here left over? Well, we have the differential dt and the reciprocal of the logarithm. So the dt is given by expression over here. So let me erase, this will look a little strange, but that's fine. Let me erase this for now because we'll grab some space. So dt becomes negative 2n pi times e to the power negative 2n pi u du. So this contribution is given by the differential dt shown over here. And then for the reciprocal of the logarithm, what will we have? We will have negative 2n pi and u. We'll put it into parentheses just to be good citizens. And what do we have over here? Well, the negative signs now, let's just separate this. We'll carefully write this equals to this, and we will move over here. So here we will have negative and negative cancel each other out. 2n pi, and 2n pi cancel each other out nicely. So what do we see over here? Well, 2n pi in the numerator, and here we have also 4 becomes 2, n becomes 1, power of n, pi becomes single power of I, same thing over here. So this guy becomes 2n pi, and same thing, 2n pi we have over here. Now 2n pi plus 2n pi, 2n pi, and 2. So these 2's, 2, 2, and 2 cancel each other out. And what do we have? If we flip the order or direction of integration, instead of going from positive infinity to 0, we go from, let's write it down, from 0 to positive infinity. What will we have? We will have this term, because of the minus over here, this term will become positive. And what will we have over here? When we carry this exponent into here, these two exponents will fight it out and disappear into a positive unity. So here we will have 1 over 1 plus u squared, this guy, we don't forget him. This guy will be with the negative sign. We'll have -1 over here. The n pi, the reciprocal of can be carried out from under the integral sign, 1 over n pi, this square bracket. And what do we have over here? I think I have, if we carry this in, so yes, I'm sorry, that was my mistake, my bad. When we carry this guy in over here, so he becomes e to the power -2 n pi u. Yes, we should not forget this guy. And over here, what is left? All this is gone, du over u. Du over u. And now this is our, let's write it down over here, this is our Fourier coefficient Bn. As a next step, what would you do? What would be your next step at this stage of our solution of this problem? Well, it may look a little scary, but here is an interesting tactical maneuver. Let's set the index in the Fourier coefficient Bn to 1. So if n is equal to 1, then what do we have? Then we have, for the value of b1, what would we have? 1 over pi, integral that runs from 0 to positive infinity. There are no n's over here, so here we have 1 over 1 plus u squared minus e to the power of what? Here n becomes 1, negative 2 pi u. And then again, the differential over the u over u. And now what do we see? Do we see our favorite Fourier integral over here? Yes, we do. How do we squeeze this guy out of these two expressions? Well, multiply this relation through by n and construct the difference. Let's write it down. So here we'll just do separate like this. N times Bn minus B1. This is what we're doing over here. We're multiplying the value of the Fourier coefficient Bn by n from this expression over here, times n, Bn, and then we're subtracting B1, this guy. So once we multiply this equality by n, what do we have? 1 over pi. Here we'll have 1 over 1 plus u squared minus this term. They will cancel each other out. This summand will be with the negative sign, but this sign will come into this summand will come in with the positive sign. So in the end, we will have 1 over pi integral from 0 to positive infinity. And here we will have, let me write it down in the very suggestive form, e to the power negative 2 pi u minus e to the power negative 2n pi u over u du. And now in that form, just about everyone should instantly recognize our favorite Fourier integral in this difference. And what is this? This will be the value of the, let me erase it over here once you guys understand what's going on here. As a refresher, just to remind all our viewers, there are probably, 2, 3 separate cases for the Fourier integrals, but under the appropriate conditions, what do we have? The integral from 0 to positive infinity, f of ax minus f of bx over x dx will be f of 0 minus f at positive infinity times log of b over a. And over here I'm abusing the notation a little bit, but it should be evident that the expression f of positive infinity is actually the limit of the function f of x when x grows without bound. And in this case, what do we see? What is the shape of the function f of x? Of course, our f of x is e to the power x. So the value of this function f at 0 is 1, at infinity is 0. This difference becomes 1, and at the end, what do we have? 1 over pi natural logarithm of, let's compute, b. In this case, let me highlight it for you. This is b, 2n pi. This 2 pi is a. b over a, 2n pi over 2 pi becomes what? N. So here all we have is n. And look at this wonderful transformation of sort. N times bn minus b1 becomes 1 over pi times the natural logarithm of n. And what does that mean? That means that for all the values of the index n greater than 1, because we know what's going on here, the values of the Fourier coefficients can be expressed as a certain value in terms of the very first Fourier coefficient, b1. So let's write it down. N times bn minus b1 equals 1 over pi, just to make it painfully obvious, logarithm of n. This is our result. And in the next segment, I will clean up the board and write it out a little bit more neatly so we will understand what just transpired. Wonderful. In the previous segment, we deduced the relationship between all the Fourier coefficients bn in terms of the very first Fourier coefficient, b1, and the expression that we had at the bottom of your right-hand side screen. I rearranged it here on the top. It's not too difficult, nothing beyond the proverbial middle school arithmetic. Everyone should be able to handle this. This relation holds so far for all n whole positive numbers, 2, 3, 4, 5, and so on. And the logical question next is, how do we unmask the name of the real number that sits behind the integral? That is the Fourier coefficient b1. Here in real time, different people will think different, will have different ideas, they will do different things. But overall, and that is precisely going back to our season 1, episode 1, the opening episode on our channel, mathematics is improvisation. So every time we take on a worthy mathematical problem, we improvise in some sense. So how we step next depends again on your personal experience, your level of mathematical maturity, and so on. Here we proceed as follows. We recall an integral representation of the Euler-Mascheroni constant shown over here. This result is not completely, again, not very difficult or horrible. It can be shown again that this is one way to represent the Euler-Mascheroni constant, and if there is enough interest in our community, I may put together episodes showing this, how this result is obtained. For now, we take it as given. We fish out this result out of our web of mathematical knowledge, and in some sense, this is the improvisational part. We put together a convincing line of reasoning. But the idea to do just that, a happy thought, has to visit us, and this is one way to proceed over here. So what do we see when we juxtapose what we have against what we need? What kind of next tactical maneuver comes to mind? Of course, we multiply this bad puppy over here by the reciprocal of pi and subtract it from b1. And in this case, what do we have? b1 minus 1 over pi times the Euler-Mascheroni constant. Let's carefully spell out what we have. 1 over pi integral from 0 to positive infinity. Let's bunch together the rational functions in both cases. Here, the first term, the rational function in u, will come in with a positive sign, 1 over 1 plus u squared, minus 1 over pi for the Euler-Mascheroni constant will come over here. So this will be minus 1 over 1 plus u, and this is it, du over u. Again, to be completely good real analysis citizens, we have to say a few words about one or two theorems which will allow us to zip and unzip these integrals and group them the way we group them, but in this case this can be done. Plus 1 over pi, the exponential terms, the integral from 0 to positive infinity. Here, let's do this arithmetic carefully. The negative Euler-Mascheroni constant times the reciprocal of pi will give us this exponential term with which sign? With the positive sign. So this guy will go here with the positive sign, e to the power minus u. The b1 coefficient here will give us the exponential term with its original sign minus. So he will write minus e to the power of minus 2 pi u, again over u, and du. And what do we see over here? Well, if you do these things fairly often on a regular basis, then you will quickly see that this integral over here actually can be computed in our mind completely. We do not need pen and paper for this one. We quickly see that this guy is 0, so he vanishes, no trouble from here. And what is this? This is the Fourier integral, making its stellar encore appearance. And let us write down, we already explained how this how the Fourier integral works in one specific case in the previous segment. Unwind or rewind to see how that works. Here we have the following result: 1 over pi times the natural logarithm of what? This over here in this case, b will be 2 pi, and what is a? A is a positive unity, so b over a, 2 pi over 1, so log, natural logarithm of 2 pi, a beautiful result. And all this things over here, all these things over here are equal to b1 minus 1 over pi Euler-Mascheroni constant equals this. So from here, what do we see? Pi in the denominator, pi in the denominator again. So we carry this guy to the right side of the equal sign, and let's write down this result over here. b1 equals the Euler-Mascheroni constant plus the natural logarithm of 2 pi over pi. This is the result. This is where our series of evaluations of integrals terminates. This is the terminal point in our journey. This is the result that we obtain over here. And now, since we know the name of the real number that hides behind the Fourier coefficient b1, we automatically know the names of all the real numbers that hide behind all the Fourier coefficients bn. If you feel comfortable with the Fourier integrals and with the evaluation of this integral and proving that this integral is actually 0, you can skip forward to our final segment. For those who are not sure why this is so, I will show a proof in the next segment. We're almost done, and this segment is optional. This segment is for those who were not sure how to handle the integral over the rational functions that we saw in the previous episode, but here it is actually quite straightforward. We do the partial fractions decomposition for the rational function 1 over 1 plus u squared times u. It's shown over here, nothing complicated. We can do this again completely in our mind. We do not need pen and paper. And over here, separately, we show the partial fractions decomposition for the rational function 1 over 1 plus u times u is shown over here again. When we construct the difference between this term and this term, what we will see? Well, we'll see these guys will, reciprocals of u will cancel out, and we will have the integral of 1 plus u minus u1 plus 1 u squared. Again, this is all baby stuff. This is not even middle school. When we integrate all this mess over here, what do we get? We get move the differential, move the 1 plus under the differential, we get the logarithm of absolute value of 1 plus u minus, once we move u, for example, u du, everyone should be able to see this, it will be differential of 1 plus u squared over 2. We don't forget to divide this by 2. So what will we have? We'll have minus the logarithm of square root of 1 plus x, sorry, it's not x, u squared. That's the result in terms of indefinite integrals. Once we use the property of the logarithms and combine these two usual suspects into one, we will quickly see that the integral from 0 to positive infinity, that looked like what, 1 over 1 plus u squared minus 1 over 1 plus u du over u. This is all this stuff over here will be what? It will be the natural logarithm, technically absolute value of 1 plus u over square root of 1 plus u squared, absolute value evaluated between 0 and positive infinity. Of course, we know that when we evaluate this limits with, when we evaluate this integral between these boundaries of integration, we should be ready to take limits. And in this case, at the lower boundary, we do not need to worry about the limits. When u is 0, the square root of this expression becomes 1. When u is 0, this is 1. 1 over 1 is 1. Logarithm of 1 is 0. At the upper boundary of integration, what do we have? U will be very large, u squared even larger. It overshadows the value of 1. Square root of u squared is again absolute value of u, becomes u over u is 1. Again, it's 1 and it's 0. So this is the result that we had in the previous segment. And now we can make the final step and write down explicitly the expression for the Fourier coefficients B1 in terms of just the real numbers shown over here. Excellent. And at this stage, we are basically and fundamentally done. All we have to do now is just write down the explicit expression for the value of the Fourier coefficients Bn, because we know all the answers. Here we take the value of the Fourier coefficient B1 multiplied by pi. Multiplied by pi, what we see? Pi and pi cancel each other out. And the numerator we will have from B1, what? From B1 we will have gamma plus, we will have gamma plus logarithm, natural logarithm of 2 pi plus the natural logarithm of n. And here we use again the classical property of the logarithmic function. Log x plus log y equals log x times y. And here we happily marry 2 pi and n and obtain the natural logarithm of 2 pi n. And look at that as an added bonus. When the value of the whole positive number n is 1, what do we have? Gamma plus logarithm, natural logarithm of 2 pi, n collapses into 1. Here n disappears into 1 pi, so we have this. So now we have a nice expression for all Fourier coefficients where n varies 1, 2, 3, and so on. And now we can simply write down the overall result, what we were asked to do in the first place. So here we will say, let's say let's do it in red also. So for all real numbers x such that they belong to the clopen subset of real numbers between 0 and 1, 0 being open, 1 being closed, what do we have? We have the natural logarithm of the gamma function of x can be decomposed into the Fourier series as follows. Logarithm of square root of 2 pi, we remember that much from the previous episodes, plus the sum that runs from 1 to positive infinity, 1 over 2n times cosine of 2n pi x plus, we remember this. Now that you guys took a careful note of this, let's erase this a little bit so we can make room for our result. We can make room for our result. So plus Euler-Mascheroni constant plus logarithm of 2 pi n over pi n times sine of 2n pi x, and we balance this over here. This is a nice and absolutely beautiful result. Let's put it into nice box. Takes quite a bit of space, but this is the result. And again, as we suggested in season 1 episode 2, where I explained how to practice mathematics correctly in one way, those of you who could not solve this problem completely correctly on your own should go back and analyze all the points where you got stuck and which maneuvers you missed. It is also beneficial to dissect this episode in terms of what was the real mathematics, what was not mathematics. We had a fair amount of mundane, so to speak, computational calisthenics. Yes, you are expected to handle all of this flawlessly, but there were some good points where we did real, actual grown-up mathematics. The first such idea was to handle the Fourier coefficients a, n in a way that avoids completely a direct computation of the relevant integral. And when we took on the integral that was the Fourier coefficient bn, we actually also made a number of clever maneuvers. One of these maneuvers was to recall the integral representation of the logarithm of the gamma function, and another such clever maneuver was to bring in an integral representation of the Euler-Mascheroni constant. We also saw how the Fourier integrals made their helpful appearance in the computations as well. This is it for the problem S2E15, and we will go to the next challenge in the next segment. Now that we have taken a short break from the dedicated study of the problem-solving approaches, and we saw how, for example, the transform and conquer problem-solving approach may work and may be applied to real academic problems and real grown-up mathematical material, we'll go back to the study of these problem-solving approaches, and starting with the next episode, we will begin the study of the equation problem-solving approach. Quite powerful too, quite popular, the approach that travels well not only throughout mathematics but throughout physics and chemistry and beyond. And in order to motivate that study, we suggest that you try your hand at solving the mathematical problem S2E15. In that problem, we're given a properly functioning analog clock whose face has 12 gradations with 12 hours as shown over here. And the challenge is to figure out how many times will the minute hand and the hour hand rendezvous in one 12-hour period. Of course, by now, we hope that all our viewers are indoctrinated enough. On this channel, we do not really care that much about the answer, as much as we care about the story behind how that answer was produced. Because remember, first and foremost, mathematics is an art of telling a story, and what we want to hear here is your story of how you solve this problem on your own. And once you do that, try to step back and see what was the big picture and what was the fundamental idea behind solving that problem in the way that you solved it. This is it for this episode. Thank you for your time. Thank you for watching. I will see you in the next episode, in which I will explain a solution of the mathematical problem S2E15.